Hi, I'm Andy and this is question 6 on the AQA Decision 1 paper from June 2009. For more questions on this exam paper, click the eye in the top right corner. In question 6, we've got a factory that makes 3 types of widget: basic, standard and luxury. The widgets produced need 3 different components, type A, B and C, and we're given a paragraph that tells us how the components of type A, B and C are used to make the different kinds of widget. And in part A, we're asked to find 4 inequalities in X, Y and Z that model the above constraints, simplifying each inequality. So before we start the question, it's always a good idea to know what your decision variables represent. So in this case, X represents the number of basic widgets, Y represents the number of standard widgets, and Z represents the number of luxury widgets. And we're told how many of each type of component is needed to make these widgets. This information will allow us to write 3 separate constraints. The first constraint we're going to do is for the type A component. We're going to write a constraint that tells us how many type A components we're going to use. So for the basic widget, it tells us we need 6 components of type A. So to make all of the basic widgets, we would multiply 6 by the number of basic widgets we make, which is X. To make a standard widget, we need 4 type A components. So the total number of components of type A for standard widgets would be 4 multiplied by the number of standard widgets, which is plus 4y. And we need 2 components of type A to make a luxury widget, so that would be plus 2z. So this expression represents the total number of type A components to make all of the widgets. And we're told that each day there are 240 components of type A available. So this total here has to be less than or equal to 240. We can do a similar constraint for the type B components. We need 6 components of type B to make a basic widget, so that would be 6x again. We need 3 components of type B to make a standard widget, so that would be plus 3y, and we need 9 components of type B to make a luxury widget, so plus 9z. And in total we have 300 components of type B available, so this must be less than or equal to 300. For type C components, for a basic widget we need 12, so that will be 12x. For a standard widget we need 18 components, so plus 18y. And for a luxury widget we need 6 components, so plus 6z. And that must be less than or equal to 900, which is the total. Next we'll look if any of these simplify. For the type A components we can see that 2 goes into everything, so we can divide both sides by 2, leaving us with 3x plus 2y plus z is less than or equal to 120. For the type B components we could divide by 3, that would leave us with 2x plus y plus 3z is less than or equal to 100. And we could divide the type C components by 6, leaving us with 2x plus 3y plus 1z is less than or equal to 150. For the final constraint, we've got this bottom line. It says each day the factory must use at least twice as many components of type C as type B. These are the type of constraints that people most often get wrong. In order to find a constraint for this part of the question, I'm going to simplify. I'm going to get rid of the at least part first. We'll come back to that later. So let's imagine it says each day the factory must use twice as many components of type C as type B. So first of all, let's write an expression for the number of type C components and the number of type B components, which we've already done here. Don't use the simplified ones. They don't represent the number of the types of component. The original equations do. So type C, which we'll have on the left hand side, is 12x plus 18y plus 6z. The 900 is not to do with the total number of components, it's just a limit on the components, it's not the actual number, so ignore that for now. For type B, we've got 6x plus 3y plus 9z. And as I want twice as many components of type C as type B, I would take the number of type B components and I would multiply it by 2. And that would give me the number of type C components. The reason people often get this wrong is because they see twice as many components of type C and think, well, I must times the type C components by 2, when actually it's the other side that you end up needing to multiply by 2. Now we'll think about this at least part that we got rid of to start with, which means we no longer want this equals sign here. And we're told the number of type C components must be at least twice as many as the type B. That means this side should be the bigger side, so we need our inequality to be that way round. But this isn't simplified yet. First thing we're going to do is multiply out this bracket on the right. That will give us 12x plus 6y plus 18z. And then we'll simplify. There's 12x on both sides, so that will cancel out. We'll subtract 6y from both sides to get 12y on this side and no y's on this side. And we'll subtract 6z from both sides to get 12z on this side. So 12y is greater than or equal to 12z, which means that y must be greater than or equal to z. And that gives us 4 inequalities. In part B, it says each day the factory makes the maximum possible number of widgets. On a particular day, the factory must make the same number of luxury widgets as basic widgets. And in part 1, it says show your answers become the following. So what this statement here is saying, the same number of luxury widgets as basic widgets, well, luxury widgets is Z and basic widgets is X. So wherever we've got a Z in one of our equations, we can replace that by an X because Z and X will essentially be the same number. And that's how we're going to achieve these equations that don't have any Z's in them. So here are our 4 inequalities from part 1. And we're interested in the case when Z equals X. So in this case, 3x plus 2y plus Z becomes 3x plus 2y plus x, and that's less than 120. That will simplify because 3x plus x is 4x, and then we can divide through by 2 to get 2x plus y is less than or equal to 60. And that's the first one here. For the next one, we get 2x plus y plus 3x, and that must be less than or equal to 100. Simplifying gives us 5x plus y on the left, and that's the same as the second constraint here. For the third one, we get 2x plus 3y plus x, and that simplifies to 3x plus 3y is less than or equal to 150, and dividing by 3 gives us x plus y is less than or equal to 50. And the final one, y is greater than z, that's just going to become y is greater than or equal to x. And there we have the 4 inequalities that we need. In part 2, it says using the axes opposite, draw a suitable diagram to enable the problem to be solved graphically, indicating the feasible region. So here are our 4 inequalities that we need to draw. We'll start by drawing 2x plus y is less than or equal to 60. To draw this line, I'm going to find the points where it crosses the axes, and to do that, first of all, I'm going to consider what happens when x equals 0, and that would mean that y equals 60. So the point 0, 60 must be on my line. And then when y equals 0, we get 2x equals 60, so x would be 30. So I need a line going through 0, 60 and 30, 0. And being as 2x plus y is less than or equal to 60, the region I'm interested in is the region below the line, so I shade out the other side of the line. Next, I've got 5x plus y is less than or equal to 100. When x is 0, we get 5x equals 100, which means x equals 20. So we get 20, 0. If we try the same method when x equals 0, we get y equals 100, which isn't on our graph. So we have to be a bit more creative for this one. Instead of thinking about what happens when x equals 0, we can think of what happens when x is a different number, any number we choose. Well, if 0 is going to go too far off the graph, we need to try something further along. For example, let's think about what happens when x equals 10. Well, 5 times 10 is 50, and 50 plus 50 equals 100, so y would have to be 50. And 1050 does fit on our graph. As we want the region where 5x plus y is less than 100, we shade the region above the line. Next, we need to draw the line x plus y equals 50, or when x equals 0, y would equal 50. But again, we have the same problem as the last one. When y equals 0, x equals 50 is too far along the graph. So let's think about what happens, let's say, when x equals 40 all the way over here. And in that case, y would have to be 10 to make it 50. So we could plot the point 40, 10. And we're interested in when x plus y is less than 50, so that means we want the region under the line, so we shade the region above the line. Our final inequality is y is greater than or equal to x, so we need to draw the line y equals x. That's a line with a gradient of 1 starting at 0, 0. So another point on the line it would go through would be 40, 40. And we're interested in y is greater than x, that means the region when y is larger above the line, and so we need to shade the region below the line. And so our feasible region is in here. In part 3 it says find the total number of widgets made on that day. Well, remember at the beginning of part B it said each day the factory makes the maximum possible number of widgets. So to get the total number of widgets made, we would do x plus y plus z. And so we could make an objective function, let's say n equals x plus y plus z, that we need to maximise. But remember, x is going to be the same as z because we're making the same number of basic widgets as luxury widgets, so this becomes n equals 2x plus y. So to draw this objective line, what I first do is choose any number that I like for n. But a sensible choice is something that's not too big or too large, and also something that both 2 and 1 go into, because that way I avoid getting decimals when I try to plot coordinates. So I could perhaps, for example, choose n equal 10. And if I do that, I would get 10 equals 2x plus y. And if I think about the coordinates where it crosses the axis, when y is 0, x would be 5, and when x is 0, y would be 10. So that would give me 0, 10, and 5, 0. But that would be quite a small objective line over here. So what I might do then is say, right, an objective line twice as big would seem sensible. So instead of n equals 10, we could just change that to n equals 20. So rather than 10 and 5, we would end up with 20 and 10. So my objective line goes from 0 to 20 to 10, 0. Now that I've got my objective line, I can use it to find the maximum number of widgets that I could make. To do that, I take a ruler and I align it with my objective line, and I move it upwards, keeping it parallel to the page until I find the last point where it leaves the region. So it's left at the top and the bottom, but it's still in at the middle, and as I get towards the end it's going to be up here. And unlike many linear programming problems in this module, it doesn't actually leave the region at a specific point because my objective line is parallel to one of the constraints. And we can see this up here, look, one of the constraints is 2x plus y is less than 60, and my objective line is also 2x plus y. And that means rather than a specific value of x and y giving us the maximum number of widgets, there are several possible combinations that would all give us the maximum number of widgets, and they're all of the points on this line between here and here. And as I can use any coordinate on the lines, I'm going to choose this point where I can see they cross on the grid lines here, which is at 1040. So I can say that there's a maximum at 1040, and therefore the total number of widgets, which we've called n, would equal the objective function here, 2x plus y, so we would get 2 lots of 10 plus 40, which equals 60. In part 4 it says find all the possible combinations of the number of each type of widget made that correspond to this maximum number. So first of all, we know the lines cross when x equals 10 here. And we're looking for all of the different pairs of coordinates that we could have between here and here that are whole numbers. Now, because I've used quite thick lines on my graph, I'm not entirely sure where this point is here. Perhaps you'll be clearer on your graph, but I'm going to have to solve it using simultaneous equations. So the two lines that I have got crossing here are 5x plus y equals 100 and 2x plus y equals 60. So if we call this equation 1 and this equation 2, I could do 1 take away 2. 5x take 2x is 3x, and the y's will disappear, and we've got 100 take 60 equals 40, which means x is 13 1/3. So that means the possible combinations will be as follows. I know that I'm allowed the x value of 10, and I'm allowed any x value up to 13 1/3. So I can have 10, 11, 12 and 13 for x. And being as x must be the same as z, that means I can put in my z values. Now I could, if I wanted, solve one of those equations up there to get the value of y each time, but considering I know that the total has to be 60, I can just see what number fits here. So 10 plus 10 is 20, that means I would need to have 40 here, which is confirmed by my answer here. And then if I make one more of each there, this would mean this would have to be 38, and then this would be 36 and 34. So these are all the different possible combinations of the amount of widgets that I could make.